Okay, well, now we're done with free body diagrams. And what a free body diagram gives you is a depiction of every force that acts on a chosen body. And now we're done with that, we're going to use free body diagrams in the most important equation of this class. So we'll use free body diagrams in Newton's second law. The most important equation in this class. And Newton's second law says that F net is equal to mass times acceleration. And we have to be careful about what each of these things mean. So I'm going to define these really carefully. F net is the sum or the resultant of all the force vectors acting on the chosen object. And this idea of defining the chosen object is a really important thing. Remember, that was the basis of why we are doing free body diagrams too, to be very clear to ourselves about what the boundary is between the chosen object and the surroundings. M is the mass of the chosen object. And A is the acceleration vector of the chosen object. So there's always a relationship between the sum of the forces acting on a body and the acceleration of the body. Another thing I want you to notice is, what does the free body diagram tell us that shows up in this equation? It tells us everything over here on the left side. Okay, if you add up all the force vectors that you put in your free body diagram, that's your F net. So your free body diagram tells you everything you know about one side of this equation, and then the other side is the only thing left that you have to deal with if you use your free body diagram right. There are two things I want you to notice about Newton's second law. The first one is you need to draw a free body diagram every time you use Newton's second law. I'm going to take points off if you don't draw a free body diagram, even if you get the question right or whatever. A lot of times, I get people who've taken physics before, excuse me, and they're not in that habit and they sort of don't like this rule. But here's what I'm telling you. If you go on in physics and end up doing complicated problems, the problems we do in physics 1 tend to be pretty simple problems. But if you go on and use this stuff for harder problems, you'll be really happy if you've gotten into the pattern, the habit of drawing free body diagrams every time. And so what I'm trying to develop here are good habits. You might have habits that have worked for you for simple problems in the past. I'm trying to help you get habits that'll work if you go on with this stuff. So draw a free body diagram for every use of Newton's second law. I'm going to abbreviate that N2L, Newton's second law. The second thing I want you to notice is, just like if you go back to the vectors homework that we did a while ago, every time you did every time you came up with a components for a vector, it first required defining a coordinate system. Well, we're going to be representing force vectors and acceleration vectors as components. And so that means that we need to choose a coordinate system before we do it. So you need to choose a coordinate system before you can represent force and acceleration vectors as components. A lot of times you might not even really notice that you're choosing a coordinate system because it's going to be the one that we're the most used to, with the x-axis pointing to the right and the y-axis pointing up. But there'll be some other times where it'll be in our, to our benefit to choose sort of a funky coordinate system. And so I want you to notice that before you can write Newton's second law in components, whether you're telling yourself this is true or not, in some way or other, you've chosen a coordinate system. And sometimes we're going to use a funny coordinate system. Okay, well, let's do a few problems. Start with the simplest ones. Today's assignment is going to be some simple ones, but let's just go through a few of these. Okay, so first of all, what if you have the ceiling and a cable that's holding up a mass? And let's say that this mass is 20 kilograms. Okay. What's the force vector that the cable is applying to the box, to the mass? So what's the force vector applied to the mass by the cable? Well, I'll start with a free body diagram of the mass. So the mass is going to be our chosen body. So there's the outline. And we know that there's a weight force applied that's acting straight down. And it has, the magnitude of that weight force is 20 times 9.81. So 196.2 newtons down. And now we look for the contact forces. So if you go around the boundary, the only place where the surroundings make contact with the boundary are at the cable, is at the cable. And that's a pulling force, so it's going to be along the line of the cable, away from the body. We don't know the magnitude of that yet. We're going to try to figure that out. So I'm going to call that T for tension. And so that's a complete free body diagram. And now we can go to Newton's second law. Like I said, whether you recognize it or not, before you can write things as components, you have to choose a coordinate system. So I'm going to choose a coordinate system, the one we're the most used to, like this. Okay, so to represent those forces as vectors, we need to figure out what the components are in that coordinate system. Well, the force of 196.2, that's down, that's in the negative y direction. So in its components, this would be 0, negative 196.2. the cable force is in the positive y direction. So that's 0 for x, positive t for y. Those are all the forces. There's the two forces. We've represented them here. So we know we're done with the left side of Newton's second law. And now we'll go over to the right side. The mass is 20. And what do we know about the acceleration vector? Well, this mass is just hanging there. It has no velocity ever and no acceleration ever, because acceleration is a change in the velocity. And the velocity is not changing, it's staying 0. And so the acceleration vector is 0, 0. And now you can break this vector equation up into an x component equation and a y component equation. The x component equation says 0 plus 0 equals 20 times 0. Okay, so that one doesn't, in this particular problem, that one doesn't tell us anything. It just gives us 0 equals 0. The y equation in this problem is the one where everything interesting is happening. And that says negative 196.2 plus t is equal to 20 times 0, so 0. And now we have an equation that we can just solve for t. T is equal to 196.2 newtons. Well, I didn't ask for the tension in the cable. I asked specifically for a force vector that's applied to the mass by the cable. So there are two ways you can do that. You can give it as the components of that force vector, which you would get from plugging this value for t back into your expression for the force vector applied by the cable. So one way you could think of this is the force on the mass by the cable is equal to 0, plug in 196.2, so 0, positive 196.2. Or another way you could think about it is we figured out that the magnitude is this. Look at the free body diagram. The force applied by the cable is pointing up. So you could think of this as a force going this direction with a magnitude of 196.2 newtons. And you should get comfortable with both of these ways of calculating those. There are different times when either one or the other might be the most useful thing for you, but those are both valid ways to give a vector answer. So that cable is pulling up on the mass with a magnitude that in this case is equal to the weight. And that's why if you've ever seen the way like spring scales for weighing fish work, the idea is you hang the fish from basically a cable that's spring loaded. And what it does is measure the tension in the spring and assume that that's equal to the fish's weight. And as long as nothing else is acting on it, as long as no one's pulling down on the fish or pushing up on the fish or whatever, that's a valid way to figure out the weight of the fish or whatever you hang from the spring. Okay, let's do another one. So for this one, let's say that there is a cart and it's moving along a horizontal surface. And let's say that it has a mass of 10 kilograms and it's being pulled to the left by a force of 20 newtons. And we want to know what's the acceleration vector of that cart. Okay, well, our chosen body is going to be the cart. So free body diagram of the cart. We have the outline there. We know there's a weight force that's equal to 10 times 9.81. And now going around the boundary looking for contact. First, there's a pushing force from the floor. I'll call that N for the normal force. And keep going around. And the only other contact with the surface is with the boundary is whatever's applying this 20 Newton force. And so now we're done. So now we'll go to Newton's second law. And again, in this case, I'm going to use the coordinate system that we're used to. In all these examples today, I'm just using the coordinate system we're used to. I'll talk about when you might want to use another one in the next lecture. Okay, so for the forces, we have the 20 Newton force that's acting in the negative x direction. So negative 20 for x, 0 for y. We have the weight force in the negative y direction, so 0, negative 98.1. We have the normal force acting in the positive y direction, so that's 0, n. And that's all the forces in the free body diagram. And so that's all the forces in Newton's second law. Easy. Now set these equal to the mass of the cart, 10. And now we have to ask ourselves, what do we know about the acceleration? Well, there is one thing that we know about the acceleration, and we're going to see that this is what we're always going to do with any kind of rolling or sliding problem. We know that this thing is confined to move along the surface. It's not going to jump up in the air, and it's not going to sink into the surface. And so what we know in this case is that this thing's acceleration is only going to be along the x-axis. Well, this is a pretty simple problem, so it's pretty easy to look at this and figure out that it's going to move in the negative x direction, but you don't even have to do that. We'll just say that it's going to move in the x direction, and which way along the x direction is going to just come out in the math of Newton's second law. So I'm going to write this as an unknown x component and a y component of 0. So the x component of the acceleration is a. The y component is 0. And now we have two useful equations. The x equation says negative 20 plus 0 plus 0 is equal to 10a. We can do the algebra, and we get that a is equal to negative 2 meters per second squared. Meters per second squared, that's the units for acceleration, and it's also the units you would get if you kept your units through the whole calculation. Now, does the y equation give us anything? Well, it says 0 minus 98.1 plus n is equal to 10 times 0. So it does give us something. We could calculate the normal force with it, but we're not asked for this. That isn't what I happen to ask for in this problem. So for this problem, I'll just leave that alone. Okay, so we calculated this variable a, but what we really want is the acceleration vector of the cart. So how do we come up with the acceleration vector of the cart from that value of the variable a? Well, again, there's two ways to represent that. One is in components, and one is an arrow with a magnitude. To get the components, just take this value for a and plug it into our acceleration vector. That circled vector is our acceleration vector. We just didn't know what a was yet. And so the acceleration of the cart is equal to -2, 0. Or you could also think of it as a direction and a magnitude. Well, you can look at these components and see that the direction is in the -x, so this way. And the magnitude of that, well, what's the magnitude of -2? The absolute value of -2, so 2 meters per second squared. And like I said, when we were calculating the force vectors in the last example, either one of these is fine. They both perfectly represent a vector. It's just one is a little more of an intuitive way of thinking about it, and one is a mathematical way if you are going to use this in future equations, which actually happens quite a bit. Okay, let me do one more example for today, and then I'll give you some problems to work on. All right, so let's say that there's an elevator, and on the elevator is a scale, and on the scale is a man. And let's say that we want to know the force that the scale applies to the man. So what's the force vector applied to the man by the scale? And we're on an elevator, so let's say that something's happening with the elevator. Let's say that the elevator is just getting up to its speed that it travels up. And for that brief instant, right at the start of the motion, there's an acceleration. So let's say there's an upward acceleration of 2 meters per second squared. And let's say that the man has a mass of 50 kilograms. What if everyone wore shirts with their weight on it? That would be terrible. Okay. So a couple things I want you to notice about this. First, the force vector that's applied to the man by the scale is the scale reading. So that's like what a scale would say the man's weight is. Okay. The second thing I want you to notice is what's the man's weight? We're doing it in newtons, not pounds, but the man's weight is 50 kilograms times 9.81 meters per second squared. That's the force gravity is applying to the man. So in other words, the weight is 490.5 newtons. And if the scale was measuring his weight correctly, the scale reading would be 490.5 newtons. We're going to see that since the elevator is accelerating up, the scale is going to be wrong about his weight. It's going to read something else. I mean, it's going to be right about that force. It's just that that force is not going to be equal to his weight because of the acceleration. And you all know from elevators, this is you have this feeling at the beginning of the motion, up or down. You sort of feel your stomach move, like something's going on. And what we're going to see here is how that acceleration that's going on changes the force that is applied to you by the ground, in this case by the scale. Okay, well, our chosen object is going to be the man. Okay. And like always, there's a weight force. And 50 times 9.81 is 490.5. And now that we've dealt with the weight force, we go around the boundary looking for where the surroundings make contact with the boundary. The only place that happens is at the ground, and it's a pushing force. So it's an upward force applied by the scale, and I'll use the variable n to represent that. And now we can go to Newton's second law. So we have, and again, I'm going to use just the coordinate system that we're used to using. Okay, so the weight, that's in the negative y direction, so 0, negative 490.5. The normal force is in the positive y direction, so that's 0, n. And these forces add up to the mass of the man times the acceleration. Okay, what do we know about the acceleration in this case? Well, the acceleration is up with a magnitude of 2 meters per second squared. Up is the positive y direction. So that's going to be 0 for an x component, 2 for a y component. Break this up into the two separate equations. The x equation says 0 plus 0 equals 0, so that doesn't do us any good. We forget about that one. The y equation, though, says negative 490.5 plus n is equal to 50 times 2. And now you can do the algebra and solve for n. And you get that n is equal to 590.5 newtons. Now, to come up with the force vector, you can put that value for n back into this vector, which represents the force on the man by the scale. Or you can look at the free body diagram and see that it's all upwards in the positive y direction. So the two possible ways to represent this are that the force on the man by the scale is equal to 0, 590.5. Or you can also think of it as an upward force of 590.5 newtons. But the interesting thing about this is, remember, the man's weight is only 490.5. So when the elevator is accelerating upwards, that scale is going to read a larger value than it would if it was just representing the person's weight. And you probably recognize this feeling from being on an elevator. When it starts to move up, you feel your knees buckle a little bit. It's putting more force on your feet, the elevator is, in order to keep you accelerating with the elevator. And when it starts to accelerate down, you get the opposite effect. You get a little bit lighter than your weight. There was one more thing I wanted to say. Oh, yeah. So this only happens right at the start of the motion of the elevator, remember. Most of the time, when you're on your way up in an elevator, it's moving at a constant speed. It's only for the first second or so when the thing is going from being at rest to having an upward velocity that you have this change in velocity that is the definition of an acceleration. Okay, that's it.